Imagine logging into websites without that constant worry about passwords, you know? Or getting loan approval without showing your exact salary.
Yeah, just proving it's like above a certain number.
Exactly. Or maybe proving you're under 30 for some grant, but keeping your actual birthday private. Sounds almost too good to be true, right? How could that even work?
It does sound a bit like magic at first.
Welcome to the deep dive. Today, we're really getting into something that makes all that possible. Zero-knowledge proofs, ZKPs. And our mission, really, is to unpack how these ZKPs manage this tricky balance between, privacy and actually proving things in our very digital world. We'll pull out the key ideas from the sources you've shared.
Looking forward to it. It's a fascinating area.
So, okay, let's start right there. What exactly is a zero-knowledge proof? Lay it out for us.
Okay, so at its heart, a ZKP is basically a cryptographic tool. It lets one person, let's call him the prover.
The one trying to prove something.
Exactly. The prover convinces someone else, the verifier, that a statement is true. But here's the kicker. They do it without giving away any extra information. Nothing beyond the fact that the statement is true.
No extra details leaked.
None. It's an idea that actually came out of MIT back in the 80s. And what's really, I think, compelling is how they tackle that fundamental conflict, openness versus privacy.
Right, like with blockchains, Bitcoin, Ethereum, they're built on transparency.
Totally, which is great for verifying transactions, for accountability, but it's a privacy headache. It doesn't really mesh well with rules like GDPR.
So ZKPs offer a way around that.
They offer a really promising path. You can validate things, check statements, but keep the sensitive stuff hidden. It's a powerful balance.
Okay, so it balances privacy and proof. But what makes it work? What are the sort of ground rules for this crypto magic?
Yeah, there are three absolutely essential properties, non-negotiable really. First up is completeness.
Completeness.
Which basically means if the prover is honest and the thing you're proving is actually true, well, the verifier will be convinced, at least with very high probability.
Okay, so honest proofs get accepted. Makes sense. What's next?
Second is soundness. This is the flip side. It means a dishonest prover just can't convince the verifier that a false statement is true. Again, with high probability.
So you can't easily fake it.
You can't easily fake it. The system should catch false proofs. And then the third one, the big one.
The zero-knowledge part.
Exactly.
Yeah.
Zero knowledge. This property is key. It says the whole process, the proof itself, leaks absolutely no extra information about the secret. Nothing beyond the bare fact that the statement is true.
Can you give us an analogy, maybe?
Sure. Think about passing secret notes in class, right? Imagine you want to prove, the note says, maybe it says happy birthday without actually showing the note. A ZKP would let you convince someone it says happy birthday, but they wouldn't learn anything else. Not who wrote it, not the ink color, not the actual handwriting, just that you know the secret message. You prove knowledge without revealing the knowledge itself.
That helps clarify it. So you prove a characteristic without revealing the whole secret. Okay, so how does this proof actually happen? The communication back and forth. You mentioned interactive and non-interactive methods.
Yeah, that's right. Two main flavors. Let's start with interactive ZKPs. These involve a bit of a conversation.
The back and forth.
Exactly. The prover sends something like a commitment. The verifier sends back a challenge. Then the prover responds with a solution or proof based on that challenge. Kind of like proving where Waldo is without pointing directly at him, just answering questions about his location.
Like that graph coloring example you mentioned.
Yeah, proving you know how to three-color a graph without actually showing the colored graph. You just answer challenges about specific parts.
But that sounds like it could be slow, maybe inefficient for something like a blockchain.
Bingo. That's the big limitation of interactive proofs, especially for blockchains. They need multiple rounds, which is slow and costly on a distributed network. And crucially, the proof generated isn't something someone else can just check later independently.
Ah, okay. So that leads us to the other type.
Right? Non-interactive ZKPs. This is what almost everything in the blockchain space uses. The prover basically cooks up the entire proof in one go, all by themselves.
No back and forth needed.
Nope. The prover generates a single proof package, sends it off, and the verifier checks it. It's just one-way communication from prover to verifier.
How does that work without the verifier sending challenges?
Well, that involves some clever cryptographic tricks. There's often this thing called a common reference string, or CRS, sort of like shared setup information.
Yeah.
And techniques like the Fiat-Shamir heuristic come into play. Yeah, it's a way to make an interactive protocol non-interactive. Essentially, you replace the live verifier's challenges with the output of a hash function. The prover calculates the hash based on their own commitments, and that hash output becomes the challenge they need to answer.
So the hash function acts like the verifier.
In a way, yes.
Okay.
Its output is unpredictable like a verifier's random challenge would be. The security hinges on that hash function behaving like a theoretical random oracle.
A random oracle, like a perfect black box for hashing.
Pretty much. Input goes in, a totally random seeming but consistent output comes out. That randomness is what makes the non-interactive proof secure. You might also hear about things like Peterson commitments being used to sort of stand in for transaction data, hiding the actual values.
Got it. So it's clear this stuff is built on some pretty serious math, even if the goal is privacy clarity. What are the key mathematical ingredients someone should be aware of if they want to understand this a bit deeper?
You're right, it is fundamentally mathematical.
Yeah.
But the rare skills book we looked at actually makes a good point. It's not necessarily super advanced math, like, PhD level stuff for many applications, but it is specific and maybe unfamiliar. It exercises a different part of the brain, as they put it.
Okay, so what kind of math are we talking about?
Well, a big one is elliptic curves. These are specific kinds of curves with really interesting properties when you do math on them over finite fields.
Geometric structures, right?
Exactly. They form what's called a finite cyclic group, and doing certain operations like finding a secret number given a point on the curve is believed to be computationally really, really hard. That's the discrete logarithm problem on elliptic curves.
And that hardness is key for security.
It's fundamental.
Yeah.
And you see specialized curves developed just for ZKPs like Baby Jub Jub, designed for efficiency within snarks.
Okay, elliptic curves, what else?
Finite fields. Think of these as number systems, where you only have a limited set of numbers, but you can still reliably add, subtract, multiply, and importantly, divide by any non-zero number.
So math still works, just within a fixed range.
Precisely. And this makes calculations very efficient and predictable, which is crucial for both performance and security in ZKPs. All the arithmetic happens within this defined field.
And hash functions, you mentioned those earlier.
Definitely. Secure hash functions, like SHA-2506, are workhorses here. They take any input data and crunch it down to a fixed size output, a hash or digest.
And they need to be secure, hard to reverse, hard to find collisions.
Exactly. Pre-image resistance, collision resistance, diffusion, meaning small input changes, create big output changes. These properties are vital. It's fascinating how these abstract concepts, finite fields, elliptic curves, properties of polynomials, suddenly become incredibly practical tools here.
Right, like the rare skills book mentions, maybe you need some linear algebra, comfort, matrix multiplication, but it's more about understanding why these specific tools are used, not being a pure mathematician necessarily.
That's a good way to put it. It's applied math, focus on these specific, powerful concepts.
Okay, so we have the basic idea, the properties, the types, the math. Now let's talk about the actual systems people use. You hear terms like snarks, starks, bulletproofs. What's the difference? What makes them unique?
Right. Those are the big three families you'll likely encounter. Let's start with ZK snarks. That stands for Zero Knowledge, Succinct Non-Interactive Argument of Knowledge. A mouthful.
Succinct and non-interactive.
Key words there. They came about around 2012. They typically use elliptic curves, and their big advantages are small proof sizes and fast verification times. Very efficient.
Sounds great. What's the catch?
The main one is the trusted setup. To get those initial parameters for the system, you need this special ceremony. And if the secret data generated during that ceremony, sometimes called toxic waste, isn't perfectly destroyed.
Uh-oh.
Yeah, someone who gets hold of it could potentially create fake proofs that look valid. It's a significant trust assumption. Plus, traditional snarks based on elliptic curve pairings are vulnerable to quantum computers.
Okay, so small and fast, but trusted setup and quantum vulnerability.
Correct.
What about starks?
ZK starks. Succinct, scalable, transparent arguments of knowledge. Introduced later, around 2018. These use hash functions instead of elliptic curves.
Ah, so potentially quantum resistant.
Exactly. That's a major plus. They rely on the security of well-understood hash functions. And the T for transparent is key. No trusted setup needed. No toxic waste.
That sounds like a big improvement.
It is in terms of trust and future-proofing. The trade-off, though, is usually larger proof sizes compared to snarks, and often higher computation costs, which can mean higher gas fees on a blockchain. But they offer great scalability and transparency.
Okay, transparency and quantum resistance, but bigger proofs. And the third one, bulletproofs.
Bulletproofs. These are quite cutting edge. They are particularly good for range proofs, proving a number is within a specific range without revealing the number.
Like the salary example earlier.
Precisely. And they're very efficient for that, sometimes needing only around 600 bytes for the proof. Like Starks, they also don't require a trusted setup.
No toxic waste there either.
Nope. And they're flexible, working with various elliptic curves, including fast ones like Ristretto. They scale well, specifically linearly with the size of the statement being proved. You see them used in privacy coins like Monero for confidential transactions.
So different tools for different needs, each with its own strengths and weaknesses regarding proof size, speed, setup, and quantum resistance.
That's the landscape, yeah.
Yeah.
Snarks, Starks, bulletproofs, each carving out its niche.
This is all really powerful stuff. So where are we actually seeing ZKPs being used today? Blockchain seems like the obvious place to start.
Absolutely. Blockchain, especially layer 2 scaling solutions for platforms like Ethereum, is a huge area. We're talking billions of dollars in value, locked in ZK rollups.
Billions, wow.
Yeah, they're fundamentally changing how we scale blockchains. By bundling transactions off-chain and generating a ZKP to prove their validity on the main chain, you get massive throughput increases and cost reductions.
Can you give some examples?
Sure. You've got systems like StarkNet, which is a decentralized ZK rollup using Starks. It's handling significant volume on Ethereum's layer 2. Then there's zkSync, which uses Snarks and aims for full Ethereum compatibility with its ZK EVM.
ZK EVM meaning Ethereum smart contracts can run on it easily.
That's the goal, yeah. Makes it easier for existing apps to move over. You also have older examples like Zcash, the privacy coin that pioneered ZK Snark used for shielded transactions. Though they've now moved to a system called Halo 2, which notably doesn't need that trusted setup anymore.
Interesting evolution.
Definitely. And others like Loopring use ZKPs for high-speed decentralized exchange trading. Polygon has its ZK EVM. Scroll's the other ZK EVM layer 2. And then there's Mina, which is unique. It's a whole layer 1 blockchain built around ZKPs to maintain a constant tiny size, like 22 kilobytes.
Just 22 kilobytes for the whole blockchain state. That's incredible.
It allows for really easy verification even on like smartphones. So yeah, huge impact on blockchain scalability and privacy.
But it's not just blockchain, is it? You mentioned earlier they have uses beyond crypto.
That's super important to remember. ZKPs are powerful cryptographic tools, not just blockchain tools. Think about online authentication. Imagine logging in by proving you know your password, but the password itself never travels over the network or gets stored on the server.
Passwordless logins, essentially.
Exactly. Or credit checks. A bank could verify your income is within a required range for a loan without you needing to show them your exact pay stubs.
Just proving the range, like with bulletproofs.
Right. Or digital identity, proving you're over 18 or a citizen of a certain country, or hold a specific qualification without revealing all the underlying details on your ID card or certificate.
That has huge implications for privacy.
Massive. And think about sensitive data sharing. Like in medical research, researchers could use ZKPs to verify that participants in a study meet certain health criteria using encrypted data without ever decrypting or seeing the individual's specific health records.
So it enables collaboration while preserving privacy.
Absolutely. It enhances compliance, helps with things like self-sovereign identity, where users control their data, improves fraud prevention. We're seeing big players explore this too, like JP Morgan or ING Bank, using ZKPs in various ways.
It really does feel like a game changer. Okay, let's get really practical now for the listener. We've seen Doc mentioned as pioneering some specific ZKP capabilities. Can you break those down?
Yeah, Doc's work really highlights how these concepts translate into user-controlled features. One big one is selective disclosure.
Selective disclosure.
It means if you have a digital credential, say a digital driver's license, you don't have to show the whole thing. If someone just needs to know you're over 21, you can just reveal that fact derived from your birth date, but keep your name, address, actual birth date hidden.
So you only share the minimum necessary info.
Exactly. You prove just what's needed, like showing you're a student for a discount without revealing your student ID number.
Makes sense. What else?
Range proofs, which we touched on. Proving a value, like age or income or even a sensor reading, falls within a certain range without revealing the specific value. Super useful.
Right. The club entry or bank offer examples.
Precisely. Then there's verifiable encryption. This is interesting. It's like putting data in a locked box where the lock itself proves something about the contents. But only specific parties, like maybe a regulator, have the key to actually open the box if needed.
So there's transparency for auditors, but privacy otherwise.
That's the idea. You might encrypt car ownership details, verifiable by anyone, but only decryptable by authorities under certain conditions. Doc offers this at the blockchain level.
Okay, what about threshold credentials?
Threshold anonymous credentials. Think of it like needing multiple keys to open a lock. A credential might require sign-off from, say, 3 out of 5 different inspectors or departments to be considered valid.
So distributed trust.
Kind of, yeah. It prevents any single entity from having sole control over issuance. Useful for things like complex regulatory approvals or maybe even group decisions, also available at the blockchain level with Doc.
And custom conditions.
Custom conditions let a verifier check if your credential meets very specific requirements without learning the actual attribute values that satisfy those requirements. For example, proving you have a specific safety certificate issued by a particular approved body, or a degree in a specific field, without them needing to parse the entire certificate content.
Wow. That's incredibly granular control.
It really is. All these features, selective disclosure, range proofs, verifiable encryption, threshold credentials, custom conditions, they all leverage ZKP principles to give individuals much more control over how their information is shared and verified.
It really feels like the practical implementation of self-sovereign identity ideas, putting the user in control securely.
That's a perfect way to sum it up. Often using public key cryptography behind the scenes to verify authenticity without revealing the core data.
Okay, this is all fascinating. Now, for the programmers listening, maybe thinking, wow, I want to build this, or just wondering how steep the learning curve is.
Let's talk about that rare skills book again. It's aimed at programmers, right?
It is, yeah. Its goal is very practical. Help a programmer build a working ZKP prover and verifier, specifically using the Groth16 algorithm, which is a popular type of snark.
But they warn it's not easy.
Oh, yeah. They're very upfront about the effort involved. They say it's definitely not something you pick up in, like, 12 days, just because the book has 12 chapters. They estimate a minimum of 80 hours of solid effort.
80 hours minimum.
And realistically, for an engineer, even with a decent math background, they suggest planning for maybe 12 to 18 weeks of disciplined self-study. It requires hands-on coding, really wrestling with the math concepts. You can't just read about it.
What kind of background help? They mentioned mathematical maturity, being comfortable with notation, understanding basics like inner products, matrix multiplication. But again, they stress it's often about tackling straightforward but unfamiliar topics. Things that feel hard because they use a different part of your brain, not because they're inherently the most complex math ever.
And what tools or languages do people use to actually build ZKPs?
There are several key ones. Circum is a popular language for writing the circuits that define the statement you want to prove. Then you have libraries and frameworks like Halo 2, Noir, which is another domain-specific language, and Snark.js, which is a JavaScript library, often used for web applications.
And the basic steps.
Generally, it involves setting up your environment, writing or obtaining the circuit definition, compiling it, generating a witness, which includes the secret inputs, using that witness to generate the actual zero-knowledge proof, and then finally having the verifier check the proof. Sometimes that verification step happens inside a smart contract on a blockchain.
It sounds involved. And with this complexity, security must be a huge concern, right? What can go wrong?
Absolutely huge. Implementing ZKPs correctly is incredibly challenging, and errors can lead to serious vulnerabilities. Because you're dealing with private inputs and complex computations, finding bugs is harder.
What are some common pitfalls?
Well, one big category is issues with the circuit logic itself. Under-constrained circuits are a classic problem where the rules aren't strict enough, allowing someone to create a proof for a statement that isn't actually true, potentially leading to things like double spending.
So the constraints didn't fully capture the intended logic.
Exactly. Or non-deterministic circuits, where the same inputs could lead to different valid witnesses, which can also break things. You also have to worry about basic programming errors amplified by the context, like arithmetic overflows or underflows within the finite fields or mismatching bit lengths, allowing sneaky input manipulation.
Simple errors with big consequences.
Very big. Sometimes, parts of the circuit might get optimized away by the compiler if they relate to public inputs that aren't directly used in constraints, which can be disastrous. There are specific named vulnerabilities too, like frozen heart, related to flaws in the Fiat-Shamir implementation allowing proof forgery.
And the trusted setup issue for snarks.
That remains a critical one. If that toxic waste leaks during the trusted setup ceremony, the entire security guarantee collapses because fake proofs can be generated. And another subtle but common bug is when a variable is assigned a value, but not actually constrained by the circuit logic, leading to potential exploits.
It sounds like auditing these systems must be incredibly important.
Critically important.
And
Difficult. We saw a hack and find a significant bug in Binance's ZK proof of reserve system. It just shows that even very experienced teams can make mistakes. Rigorous security practices, thorough audits, better tools, safer libraries, formal verification, these are all essential.
so it's powerful tech, but needs very careful handling.
Definitely. The potential is enormous, but so is the complexity and the risk if not implemented correctly.
Okay, so let's try and wrap this up. We've covered a lot of ground. The core takeaway seems to be that zero-knowledge proofs, their generation and validation, are genuinely transforming how we think about privacy and verification, especially in decentralized systems, but also way beyond.
Yeah, they offer this really elegant solution to that old tension between needing transparency and needing confidentiality, a way to bridge that gap.
And for you, the listener, the potential is huge. It means things like truly secure digital identity, much better protection for your sensitive data, and building trust online in ways that actually preserve privacy, from banking, voting, just everyday web use.
It really touches almost everything we do digitally, which leads to maybe a final thought to ponder.
Go for it.
Given how powerful and, yes, complex ZKPs are,
Yeah.
how do you think this technology might fundamentally change what we expect regarding digital privacy and trust, not just in Web3, but in every online interaction over the next, say, 10 years? What parts of your own life, personal or professional, might look completely different because of this?
That is a powerful question to leave everyone with, something to definitely keep an eye on as this technology continues to evolve. Thanks for breaking it all down.
My pleasure. It's a fascinating